In this video, I'm going to introduce you the universal law of gravity. So gravity. So gravity, gravitational force. Let me see. We've been saying gravitational force. We use the Fg, right? And that's the magnitude of a gravitational force is mass times gravitational acceleration, right? This little g is called gravitational acceleration. Gravitational acceleration. And we say g is 10 meter per second square. We use, actually, the value of a g is 9.8 meter per second square on Earth. But, so this is the gravitational force and it's always vertically down and the magnitude is mass times g, little g. But this little g actually varies. Varies. So for example, like I said, g equals 9.8 meter per second square near the surface of the Earth. But we know that there is a gravitational force on the moon, and that's the little g is going to be 1.622 meter per second square on the moon. Actually, even on Earth, if you go up to the top of the Everest, 9.7639, this little g acceleration decreases as farther away, you go farther away from the Earth. At the top. Not. So this little g is not constant. So at the top of the Everest even, so here's the Earth. So if you go a little bit farther away from the Earth, the little g decreases. On the surface of the Earth, 9.8, just a little bit away, it's 9.7. So this little g is not a constant value. It depends on the location. Here we have new law, and this is the universal law of gravity. Just going to write you what it is. Fg equals to some kind of a constant g, m1 times m2 divided by d squared, where this big G is the universal constant, universal gravitational constant. So this big G does not change. It's not depend on the location. It's always this. The value of a G is 6.67 times 10 to the minus 11 Newton meter square kilogram square. And let me just put this together. Here is the universal law of gravity that you can apply to any objects that has mass. So every time you have a mass, m1, by Newton's what law? Newton's third law of motion says that every time you have two objects, force applied on one, same force but opposite direction applied on two. So you have a m1 and m2. Every time you have a mass, you're going to have a gravitational force. This gravitational force among each other applies towards each other as an attractive force. Gravitational force on m1 due to m2 is going to go towards m2. Gravitational force on the m2 due to m1 goes towards m1. So it's attractive force. Attractive force, and the value, the magnitude is the same. G m1 m2 divided by d squared, which is the distance of the two objects, square, inverse square. So anytime you have m1 and m2, you have one object that has a mass m1, you have a second object, the mass m2. And when they are separated by distance d, this is the distance. There is going to be a gravitational force due to the mass of m1 and m2, and the distance squares depends on that, inverse distance square. And there's going to be a gravitational force applied on m1 towards m2. The same amount of gravitational force applied on m2 towards m1. And its attractive force it's the same magnitude, Fg, Fg, and again, Fg is equals to this universal gravitational constant, 6.67 times 10 to the minus 11 times m1 times m2, the mass of the two objects in kilogram, divided by the distance square towards each other. All right. So example. Let's see, we have, again, the apple. On Earth. Apple on Earth. Where's the apple? I thought I had an apple. So let's find the gravity. Let's apply this universal law of gravity, Fg. Between the apple, this is going to be between apple and Earth. This gravitational force on the apple is equals to G, the mass of the apple, mass of the Earth. And the Earth is so large, so it could be maybe 1 meter away from the floor, the ground. It could be even 10 meters above the ground. But you can approximate the distance to be the radius of the Earth. So here is going to be the RE, the radius of the Earth, from the center of the Earth to the surface. Because the Earth radius is so large. So this is going to be the gravitational force on Apple due to the Earth, and also the gravitational force on Earth from the Apple. Newton's third law says equal and opposite each other, and these are the pair. So you're going to have a force on Apple, right, towards FG, and then the Earth also have the same amount towards the Apple. It's attractive force. Let's see. Let's put a value in. So we say, we know the mass of the Earth. So mass of the Earth, that's equals to 6 times 10 to the 24 kilogram. Accurately, it's more like 5.972 times 10 to the 24 kilogram. All right. And radius of the Earth, that's 6.4 times 10 to the 6 meter. More accurately, 6.365 times 10 to the 6 meter. 64, 600, yeah, it's okay. So 6.365 times 10 to the 6 meter. So we know this is just the mass of the Earth and then the radius of the Earth. Let's see. So on the Apple, gravitational force is applied. And this gravitational force, Fg, we said, that's equals to G, M of the Apple, mass of the Earth, radius of the Earth, square. And I can put the mass of the Apple outside and put these constant as 1 square. Big G is 6.67. Big G is 6.67 times 10 to the minus 11 Newton meter square kilogram square. Is that right? Yeah. And then that times 5.972 times 10 to the 24 kilogram, the mass of the Earth, divided by radius, 6.365 times 10 to the 6 meter square. All right, calculate this. Put these in your calculator. So here, you see on Google, you can just put calculator. So I already put it, 6.67 times 10 to the minus 11, which is the G, big G, universal gravitational constant, times 5.972 times 10 to the 24, the mass of the Earth, divided by radius of the Earth square, 6.365 times 10 to the 6. Answer is, what do you see? 9.8. What is that? Right? It's 9.8. So you calculate it and then you should see. Are you seeing it? Okay, good. All right. So this was 9.8, remember? And let's see the unit. Newton meter square divided by kilogram square times kilogram divided by meter square. So you see these meter squares cancels. One of the kilogram cancels. So what we have here is Newton divided by kilogram. Newton is kilogram times meter per second square. Newton's second law of motion says meter per second square equals Newton divided by kilogram. So Newton is kilogram times meter per second square divided by kilogram. What do you see? This is meter per second square. The acceleration. What's that equal to? The little g that we use on the surface of the Earth. Right? So you see that the universal law of gravity works between apple and Earth. You can have an apple or moon. You can apply to between the two astronomical objects, sun and Earth, moon and Earth. Or let's look at two particles, like a granular particles, between the two fundamental particles. Any object that has mass gonna have a gravitational force attractive towards each other. You're always gonna have a force between each other. Any objects. So the pen drops. There's a gravitational force on the pen from the Earth, and then the Earth is pulling the pen up. But at the same time, let's say I have a mass. Pen has a mass. So between myself and a pen also have a gravitational force, attractive. But since the mass of the Earth is so much more, that's just not, and compared to the mass of the Earth, the gravitational force between a pen and the Earth is so much more between the gravitational force between myself and a pen. So you don't see anything happening. Pen is not going to be attracted to me. We don't have as much of a gravitational force compared to the Earth, right? If I let go of the pen, it doesn't come to me. It goes to the Earth because that's bigger. But in fact, every mass have an attractive force each other. You're always going to have a gravitational force among each other, attractive force. All right, I'll see you at the discussion.